Today's topic is the mysterious number e, and in particular, why e is the best base for exponential functions. Like pi, e is an irrational number. It's approximately 2.71828, and those numbers trail off to infinity, never repeating. Today we're concerned with the question, why is the number e so special? You're aware of the fact that the exponential function e to the x is called the natural exponential function. Now that base e, 2.71828 approximately, is bigger than 2, but slightly smaller than 3. So this natural exponential function lies above the graph of y equals 2 to the x, but below that of y equals 3 to the x. And if you reflect the graph across the line, y equals x, you get the graph of its inverse, which is the logarithm to base e of x. And we denote that as ln of x, and you know that we call that the natural logarithm function. So today's questions will be, what is so natural about the natural exponential function e to the x? What's so natural about the natural logarithm function, ln of x? And in general, what's so special about the base e? I'll convince you with a compelling argument that e is the best base that you could possibly have for any exponential function. You can't be better or more efficient than e. As a point of departure, we'll consider a related question. What's the best number system base? Now, on this slide, I'm going to remind you of the basics of number systems to different bases, and then we'll move on from there. We use the base 10 number system. The base 10, or decimal number system, uses 10 digits, 0, 1, 2, up through 9. And we encode any number as a sequence of these digits. For example, the number 1017 is denoted by a sequence 1017 because this number is 1 times 10 cubed plus 0 times 10 squared plus 1 times 10 to the 1 plus 7 times 10 to the 0, or 7 times 1. So 1, 0, 1, 7. You can have a number system base to any positive integer. You're probably familiar with the base 2, or binary number system, which uses 2 digits, 0 and 1. As an illustration, consider this number 1017 and what its binary representation would be. Now, 1017 is 1 times 2 to the 9th, plus 1 times 2 to the 8th, plus 1 times 2 to the 7th, plus 1 times 2 to the 6th, plus 1 times 2 to the 5th, plus 1 times 2 to the 4th, plus 1 times 2 to the 3, plus 0 times 2 squared, plus 0 times 2 to the 1, plus 1 times 2 to the 0. So when you collect these bold coefficients for the powers of 2 that add up to 1017, you get this particular binary representation for 1017. So any integer and binary representation is a sequence of zeros and ones, just like any number in base 10 is a sequence of digits 0 through 9. If you're a computer scientist, you also know about the base 16 hexadecimal system. It uses 16 digits. It starts off with 0 through 9, but it continues with A, B, C, D, E, F as digits, and A represents 10, B is 11, C is 12, D is 13, E is 14, and F is 15. So that's 16 digits altogether, including 0. So take 1017 as an example. When you write it in terms of the powers of 16, it's 3 times 16 squared plus 15 times 16 to the 1 plus 9 times 16 to the 0. Now, in the hexadecimal system, this 15 is represented by its own digit f. So we have 316 squared plus f16 plus 9 times 1, which gives the hexadecimal representation 3f9. So just 3 digits encode the number 1017 in hexadecimal. There have been a lot of cultures throughout civilization that used number systems to bases other than 10. Most famously, perhaps, the Babylonians used base 60. The ancient Babylonians had 60 cuneiform digits. Now, they didn't have a 0. They weren't that advanced, but they used a blank for 0. So if you include that blank, that's 60 digits. And here they are, the cuneiform representations or digits for the numbers 1 all the way up to 59, and then the blank is 0. So just as an illustration, again, 1017, to get its representation in the Babylonian cuneiform system, we write it in terms of powers of 60. It's 16 times 60 to the 1 plus 57 times 60 to the 0. And let's see, 16 is this particular cuneiform symbol, and the 57 is this one. So that's this cuneiform number times 60 plus this one times 1. So this number 1017 is represented by these sequence of 2 cuneiform digits in the Babylonian base 60 system. So the takeaway from this is that anytime you have a positive integer n, you can have a base n number system. In general, the base n number system uses n digits or symbols, and numbers are represented by strings of those n digits or symbols. And if you think about it, a k-digit long base n number is capable of representing n to the k different numbers. So for example, in base 10, if we say, let's make k3, a 3-digit long base 10 number, it's capable of representing 10 to the 3 or 1,000 different numbers. They would be starting with 000 all the way up to 999. That's 999 plus 0, and that gives you 10 cubed, or 1,000 different numbers. Is there one base that's better than all other bases? To answer that question, think about the best number system base for a phone. Our phones are, of course, base 10. They have 10 buttons. Our phone numbers happen to be 10 digits long. So if you think about it, that gives us the capacity for 10 raised to the power of 10, or 10 billion different phone numbers. If our phones were binary, they'd only have 2 buttons, a 0 and a 1. And our phone numbers would be strings of zeros and ones. And you might imagine that a binary phone number would be longer than 10 digits that we use for our phones. Now, of course, the Babylonians didn't have phones, but if they did, their phones would have 60 buttons. They might look something like this. Now, let's think about how long a phone number would have to be in base n. And let's say you wanted 10 to the 10, or 10 billion different phone numbers. To get 10 to the 10 phone numbers, a base n phone number would have to be k digits long, where n to the k equals 10 to the 10. Now remember, for base n to the k is how many different numbers can be represented by a k-digit base n number. And we want that to be 10 to the 10, or 10 billion. To figure out that length k of a phone number, we'd solve this equation. take the log of both sides to bring this exponent of k down in front. So you get k log n equals, this is log base 10 of 10 to the 10, that would be just 10. And finally, we could solve for the length k by dividing both sides by log n. So to summarize, to get 10 to the 10 phone numbers, a base n phone number must be 10 over log n digits long. So for instance, think about binary phones. Base n equals 2. How long would those phone numbers have to be? Well, they'd have to be 10 over log of 2 digits long. And if you calculate that, it works out to be 34 digits long. So we'd have to have 34 digits in a binary phone number. Now, what about a Babylonian phone? Base 60. How long is the phone number? Plug in a 60 right here, 10 over log 60. If you work that out, you get 6 digits, which makes sense. They had more digits, more buttons, so you'd expect their phone numbers to be a little bit shorter than our 10-digit phone numbers. Now, more buttons means more choices each time you punch a key. Slightly more mental effort, and a greater chance for mistakes. More buttons is more complex, more of a hassle. But compound that by the number of digits in a phone number. Let's define the base n hassle index to be the number of buttons times the length of the phone number. That is literally how many choices you have to make to dial a phone number. The number of choices per punch times the number of times you have to do that, the length of the phone number. It's literally the number of choices you have to make. Lower hassle index would be easier to dial, less chances of mistakes. Higher hassle indexes mean it's more mental effort to dial and more of a chance to make mistakes. That hassle index would be the number of buttons, which would be n for base n, times the length of a phone number, that's 10 over log n. So n times 10 over log n, so our base n hassle index is 10n over log n. So the best base is the one with the lowest hassle index. And what base would that be? Let's find out by graphing the hassle index. We'll use a coordinate system where the horizontal axis is n, the number system base. So here you see bases 2, 3, 4, 5, up to 10. And if you graph 10n over log n, the graph looks something like this. Now, the number system base has to be a whole number, but interestingly, you can graph this expression, this function, 10n over log n, for real numbers. And that's what we've done here. It's a smooth, unbroken curve. And you can see, for example, and compute that for the base 10 number system, we get an index of 100. But look at this, base 2 is significantly better. The index is 66.4. And base 3 is even better than that, just slightly lower. In fact, it looks like that's as low as you can get for a hassle index for a number system base. So our conclusion, at least for now, is that base 3 is the most efficient number system base. But wait a minute. There's a point somewhere between 2 and 3. It's not an integer, but it looks like the hassle index is as low as it could possibly be there. And that point is E. E is the number that gives you the lowest possible hassle index. It's where the graph of the hassle index bottoms out, right there at E. And later, when you have more calculus, you can actually prove that this is exactly E at this lowest point. So what base has the lowest Hassel index? Answer, E. E is the one. E is the best base. Now, of course, this conversation is a little bit silly because a number system base has to be an integer. It can't be an irrational number like E. But our discussion actually illustrates a deeper truth. In a very real sense, E is the most efficient base. And this will become abundantly clear as you study calculus. In calculus, the idea of a derivative of a function is paramount. Now, at this point, you may know what a derivative is. You may not. Don't worry about it. You don't have to know. But suffice to say, a derivative of a function is another function that tells you the slope of a tangent line to the original function at any point. And you'll spend a lot of time in calculus developing formulas for derivatives of various functions. One of those formulas will be the derivative of the exponential function a to the x, and d dx means derivative. So derivative of a to the x, you'll learn, is the function a to the x times ln of a. Now imagine that that base is not just a generic a, but it's the specific e. The derivative of e to the x would be e to the x times ln of e, and ln of e is 1. You're going to get the derivative of the natural exponential function e to the x is itself e to the x. Look how much simpler the formula is when you have base e. Compare the answer a to the x ln of a with the simple answer e to the x. So we get a much neater derivative if the base is e. Now for logarithm functions, you'll develop a rule that says the derivative of log a of x, the derivative of that function, is 1 over x times ln of a. Now if we have base e, that ln of a is ln of e, which is 1. So the derivative of log base e of x is the function 1 over x. Look how much simpler that is when you switch from a generic base a to the specific base e. It's much simpler. And we would write this as the derivative of ln of x equals 1 over x. So the takeaway from this is that calculus with e is really nice. Formulas will be neater, computation simpler if you use e. It's the best possible base for an exponential function. So if you invest some mental energy now in understanding e and becoming fluent with ln, good things await you in calculus. If this has been helpful, take a look at my Calculus 1 webpage, search for Richard Hammack's Calculus 1, or go to this link. Goodbye.